1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the numbers that everyone is familiar with. It is called the base 10 system because there are 10 digits, 0 through 9. Each digit left in a number is that digit times another 10. The 3 in 309 is worth 300. This is kindergarten stuff. Very obvious. But what about when we start changing the base? 1100100. This is the number 100 in base 2, also known as binary. In binary, there are only two digits, 0 and 1. While it may seem inefficient to us, to computers this system is super useful. Computer hard drives encode data with the direction of tiny magnetic fields. To stay accurate, the magnetic fields just go in two directions. Any more and slight skewing could corrupt data. 64. This is the number 100 in base 16, also known as hexadecimal. Hexadecimal has 16 digits and is also useful for computers. Have you ever seen the RGB color system? Each color, red, green, and blue, have a value between 0 and 255. Those values can be expressed by a two-digit hexadecimal number. That is why color codes have letters in them. The letters are extra digits in the hexadecimal system. Hexadecimal is useful because it can condense binary fourfold. 255 in binary is 11111111, and in hexadecimal it is just FF. Both base 2 and base 16 have a use in computers, but what use does base 10 have? Many people think that we use base 10 because of our 10 fingers. In fact, digit is another word for finger. If you look at 10 critically, however, you may find little use in it. The number 10 only has the factors 1, 2, 5, and 10. That is not a lot. The number 12 has the factors 1, 2, 3, 4, 6, and 12. That is a lot more. That is why some people think we should count in base 12. It would make basic division easier, and it would make multiplication tables easier. In base 10, 1/2 equals 0.5 and 1/5 equals 0.2. Those are the only easy ones. If you try 1/4, you are greeted by 0.25, and 1/3 is an infinite string of 3's. And don't get me started with 1/6. Base 12 fixes this. In base 12, half equals 0.6, a third equals 0.4, a fourth equals 0.3, and a sixth equals 0.2. This sacrifices the niceness of 1/5, but at a great benefit. Also, the multiples of 3 would be a lot simpler to remember. Basically, it sacrifices the niceness of 5 for the benefit of other multiples. So, should we use base 12? Probably, but getting 7 billion people to overhaul the entire number system they use, as well as change all previous uses of base 10, would be so time and cost intensive that it won't happen. Think about it. Every library book, every website, computer programs, clocks, blueprints, all needing a change. We would also have to change the metric system so that it follows the powers of 12 and not 10. This would require a change to all meter sticks, all distance measurements, and all of the other tens that the metric system uses. In the end, there are many different base systems that we use for either practical or not so practical reasons.